In this presentation, we're going to discuss the total response of a system. We'll review what we've already learned, we'll look at an example, and then we'll talk about how it relates to what you learned in differential equations. So let's remember what we know about the total response here. Total response is a zero input response plus a zero state response. And we learned how to find the zero input response and the zero state response earlier. The zero input response was the sum of the characteristic modes, and the zero state response was the convolution of the impulse response and the input. So we have the equation that y of t equals the sum of k equals 1 to n, where n is the number of modes, ck e to the lambda kt plus h of t star x of t. And at this point, let's remember also how important the characteristic modes are. You see them here, they show up in the zero input response, but remember also that they're showing up within h of t as well. So these characteristic modes will be extremely important to looking at the total response of a system. Now we've studied how to find all the terms on the right hand side, so you should feel comfortable with this material. Let's look at an example problem and see how it works. So here's the example we'll study. The differential equation is y dot plus ay equals bx, and a is going to be greater than 0, and so will be b. The input x of t will be a unit step, u of t. And this is a first order differential equation, so we only need one initial condition. The initial condition is y at time 0 minus is equal to r. And r is just some number. We're not going to specify it right now. I want to keep track of how this initial condition propagates through the solution. So I don't want to give you a particular number like 5 or 3 here, because I want you to see how it fits into the solution in the end. So our differential equation can be written in the form d plus a times y of t equals b times x of t using the differential operator. And you see that q of d is d plus a and that p of d is b. And our characteristic polynomial then is q of lambda is lambda plus a, and we set that equal to 0 and find the characteristic value lambda 1 equals minus a. And because this is a first order differential equation, we have one characteristic value and one mode. So now let's find the zero input response. We write y0 of t is c e to the minus at, because we know that the zero input response is going to be the sum of the modes, but there's only one mode here. We put in the initial condition y at time 0 minus is equal to r, and we should note that y at time 0 minus will be equal to y0 at time 0 minus, since the input is occurring at time 0, and therefore at time 0 minus the total response is equal to the zero input response. So y0 at time 0 minus is equal to r, which tells us that the constant in y0 of t equals c e to the minus at. That constant c is equal to r. So we have y0 of t equals r e to the minus at, where r is the specified initial condition. Now we'll find the response due to the input, and for that we need to find the impulse response so that we can do the convolution of that with the input. So we'll recall the differential equation. It was d plus a times y of t equals b times x of t. We'll note that there's one derivative of y, so n equals 1, and there's no derivatives of x of t, so m equals 0. And since m is less than n, the impulse response h of t will not have an impulse at time t equals 0. So, therefore, h of t is the sum of the characteristic mode terms. We can now find h of t using the method that we outlined before. H of t will be equal to p of d times yn of t multiplied by u of t. We recall from the differential equation that p of d was equal to b, a constant, and now we need to find yn. And for that, of course, what we need to do is to match the appropriate initial conditions for this problem. The initial conditions here not being the actual initial conditions, but the special ones that are dictated by the simplified impulse matching method for finding the unit impulse response. Now, since we have only one characteristic mode, we know that we'll only need one initial condition from the impulse matching method. The mode was yn of t equals c e to the minus at, and since n equals 1, as I said, one mode, we have to select yn at time 0 equals 1. And of course that means that c is equal to 1. So we find yn of t equals e to the minus at. Now from the impulse matching method, we know h of t is the quantity p of d times yn of t multiplied by u of t. So plugging in for p of d, that's b, and yn we found to be e to the minus at, we have h of t equals b e to the minus at u of t. So now we've found the zero input response, which was r e to the minus at, and we have the zero state response, which is h of t convolved with x of t. H of t was b e to the minus at u of t, and x of t was u of t. So all we have to do is perform this last convolution, and we'll find the total response for this problem. Now when I write the zero input response as r e to the minus at, you notice I don't have a u of t there, and that's because it's understood that this response is for time only greater than 0 minus. It's best if we explicitly note it in writing next to the expression that t should be greater than 0 minus. So now we find the convolution between our h of t and our input, which is u of t. And we use the convolution table for that, and we find the result to be b over a quantity 1 minus e to the minus at times u of t. So we add that in with our zero input response, and we have our solution to our problem. Y of t is r e to the minus at plus b over a times the quantity 1 minus e to the minus at u of t. And we note that this solution is good for time greater than 0 minus. The first term with the r in it is the zero input response, and the second term with b in it is the zero state response. And here I've sketched these two responses, the first one being the zero input response, the second one being the zero state response. So the zero input response is this decaying exponential. It starts off at r at time 0 minus, and the zero state response is a curve that starts off at 0 at time 0 and proceeds up to b over a. Now you'll note that both the zero input response and the zero state response contain the term e to the minus at. So we can collect these terms and write this solution instead as y of t is the quantity r minus b over a times e to the minus at u of t plus b over a times u of t. And what we've done here by grouping these terms is we've recovered what we call the characteristic and particular solutions that you had back in differential equations. The characteristic solution had the form of the characteristic mode, and the particular solution had the form of the input that was acting upon the system, the non-homogeneous term. The problem with this way of writing the response is it obscures the contributions of the individual terms, that is, what the input caused and what the initial condition caused. So in general, we will not refer to the characteristic and particular solutions, and instead talk about the zero input solution and the zero state solution. So here we're going to do a little total response review, and I'm going to try to put everything we've learned about total response kind of in just a few minutes, because students have often said that the material is spread out over several lectures and it's hard to understand it all. So first, the total response is the system output due to both initial conditions and the input x of t. And for a linear system, the total response is the zero input response plus the zero state response. So our job in finding the total response is to find these two different quantities, the zero input response and the zero state response. The zero input response, of course, is the system's output due to initial conditions alone. So the input x of t is 0 and has no effect on the output when we're determining the zero input response. On the other hand, the zero state response is the output due to the input alone. The initial conditions are all 0 when determining the zero state response. They have no effect on the output. Now this rather complicated slide completely sums up all the aspects of finding the total response. So on one side, we have the process for finding the zero input response, and on the other, we have the process for finding the zero state response. We start off with the differential equation. Q of d times y of t equals P of d times x of t, and we're giving some initial conditions, y and y dot and so on, at time 0 minus. We then proceed either down one path or the other to find either the zero input response or the zero state response. The zero state response is found by the process given on the left-hand side of the diagram. The zero input response is found by the process on the right-hand side of the diagram. So let's start with the zero state response on the left-hand side. First, we have q of lambda equal to 0. That's the characteristic polynomial. We solve for the roots, lambda 1 through lambda n. Then we'll find the impulse response. To do that, we solve the following problem. We're going to find yn of t. Yn of t is a special solution of the differential equation q of d y of t equals to 0. It's a special solution because we have some special initial conditions. We have yn at time 0 equal to 0 and all the derivatives at time 0 equal to 0 except for the n minus 1th derivative of y, which we set equal to 1 at time 0. Once we find yn, we're ready to find the impulse response. H of t is equal to b naught times delta of t plus the following quantity, p of d operating on yn multiplied by u of t. I'll point out here that b naught is the lead coefficient of the polynomial p. When we have the impulse response, we can then do the convolution of that h of t with our input x of t to find the zero state response. Now with the zero state response determined, we can then find the zero input response, and that's on the right-hand side of our diagram. We take in all the initial conditions, y at time 0 minus, the derivatives at time 0 minus, and we find the solution to q of d y of t equals 0. That solution is going to be a sum of characteristic modes. So we simply need to find the coefficients ci so as to satisfy all of the initial conditions. Once we've found those coefficients, we would then have the zero input response. And with the zero input response and the zero state response, we can add those together and we can find the total response. If you're thinking this is a rather onerous process, you're right, it is. Fortunately for us, we can do this much more easily after we learn the Laplace transform. One thing that often confuses students is the use of very similar methods on two sides of this diagram. On both sides, we'll find y0 or yn as the sum of the characteristic modes with undetermined coefficients. And then we find these coefficients by satisfying initial value problem. On the right-hand side, step 2, I've labeled here, these are the actual initial conditions from the problem. On the left-hand side, step 1 labeled here, these are not real initial conditions. These are sort of fake initial conditions, which are useful for finding the impulse response. So please don't confuse these two different parts of finding the total response.